Hello and welcome to the Engineering Dynamics Course Companion. Today is Class 9. We're continuing with the kinetics of particles. This is work energy method and conservation of energy. This is part 2. I'm Newt Dog and this is my pal Wormy. We are your course companions. Reminder that you could go down to the description below and there's a table of contents and you could just click and go to the example right away. I think we don't have much more in this class. Okay, yes. So the bottom line up front, what we talked about in the last class was we have this work energy equation, which is made up of the kinetic energy and potential energy at the beginning, some external work that's happening between states 1 and 2, and then the total energy at state 2, right? So we have the energy before, something happens to it, the energy after. Conservation of energy is really this trade-off between potential energy and kinetic energy, right? If there's no external work happening to it, there's the conservation of energy. It's conserved. I don't think I have an example that goes through this in this particular one. There is in the book, but efficiency is the energy output divided by the energy input, or what you want over what you paid for. And we also define power is going to be the time rate change of work, so it's relevant here. So we have force times the distance something travels per time, which is force times velocity, right? So that's an important concept. We'll also see when we go to rotational things in rigid bodies that we could also have torque times the angular velocity, or torque times RPM is another way we could save power, right? So maybe if you're on a ship and you have hull resistance times the speed of the ship, so you have resistance times speed, that's force times velocity, that's going to be power. Or it might be in a jet aircraft, you might have the jet thrusters in order to travel at a constant speed. You could have the balance between the thrusters and the air resistance, that net, that force that's being applied there. That force times velocity is also going to be the power, right? It's not the net, right? Well, if it's traveling at constant speed, the air resistance and the thrust force will be equal to each other. So it's one or the other times the speed, and that's going to be the amount of power. Okay, so work energy problems usually have this type of thing where, the typical problems, we might have a conservation of energy problem, and that's really a balance between potential energy and kinetic energy. So there's no external work. And then we might have external work that's applied. We might have friction energy loss, and we saw that in the last example in the last class. We might have multiple particles. We want to take a look when that happens. We might also have some power and efficiency things that are happening. And as I mentioned, efficiency is a definition is energy output over energy input, right? Or what you want over what you pay for, right? And so I think the law of thermodynamics, the first one is you can't get something for nothing, and the second law is you can't even break even, and that's what efficiency comes into, right? That there's always a price to pay for just changing from one form of energy to another. Another way to say is we could take 1 is going to be minus the energy loss divided by the energy input. All right, so here's our problem. It's got a little bit more complicated problem where we're going to have multiple stages going on. And so we have this, once again, a block, and there's no external forces taking place here. But there is friction, right? So friction is going to rob some energy. So this is not a conservation of energy problem. So the spring has a spring rate or stiffness of 25 kilonewtons per meter, and it's used to stop a 75 kilogram package that is moving down the theta equals 60 degrees incline with an initial speed of 3 meters per second. When it is 10 meters, right, from the spring, right? So it's starting out 10 meters away from the spring and going down this slope. The coefficient of kinetic friction between the package and the incline is 0.2. And we want to find the maximum distance up the incline that the package will travel after it bounces off the spring. And we want to know what is the efficiency of this process, right? So this block is coming down, right? And it's going to compress the spring It's going to stop, pause a little bit, and then the spring is going to push it, and then the block is going to travel back up the slope, right? And we're going to figure out what's the efficiency of the process. So if it was perfectly efficient, right, that block would go right back up to its original position at its original speed, but it's not going to. It's going to come up someplace, and it's going to stop. What we suppose it is. So we use Newton's second law to find the force in the y prime direction, because we want to get the normal force, because we need that to get the friction. And you notice the direction of the friction. We put in the inertial body diagram, although we're not going to check anything on that side of it, but it's good practice to put it in there. So anyway, we work through and we find out what the normal forces are. Be careful with our angles. And we figure out what the friction force is once we have that. So this is gonna benefit us if we solve it in 3 states. So we're gonna start with a state 1 where it starts at the top, right? So state 1, and then we're gonna state 2 is when the spring is completely compressed, right? And our initial goal is to figure out, okay, how much does it compress? And we'll use that as the datum, right? So it's nice to it's nice to go to the very bottom to use the datum right here. So between states 1 and 2, we have this fundamental equation, work energy equation, and the distance that it is from the datum at state 1 right here. So I'm using this bottom corner, right? So sometimes we want to use the center of it. You just want to make sure we're using the same spot, but it's going to be easier to use the bottom corner of the thing as our reference. So we figure out what y1 is going to be, right? Make sure we have the angle involved. We know what the kinetic energy is going to be at state 1. It's given to us that it's at 3 meters per second. And we know the potential energy is going to be that y1 of state 1. And then we know that the friction, the work that's acting on it, that external, is going to be the friction force times the delta x in the x prime direction. So that's going to be that friction force, and it's going to be d plus delta, right? The kinetic energy, when it's going to stop, it's going to pause when that spring is completely compressed, and at that moment when it's compressed like that, we're going to find that it is the potential energy, right? So there's some potential energy because the spring has now compressed and is storing some energy when the thing has paused. So we go ahead and write that out, and we put some values into it, right? Let's see. We bring that out over to here. Oh, when I think I skipped a step. I don't usually do that, or maybe it's just not onto the slide. But if you take a look right here, we have a del, and we have a del, and we have a del, but one of them is a del squared. If we plug in all the values that we know for this thing, we get a quadratic equation, right? So we want to find the roots with a root solver, or to take the quadratic equation, and we go in here and we get a positive value and a negative value. That negative value is physically meaningless, right? So we want to be careful that we don't think too hard onto this. There's a extra part into this thing. So here's what the del is, and we needed to do this second. We in a lot of problems, we might have been able to go from state 1 to what we're going to call state 3 in a second. But we needed to figure out that del because that also contributed to some of the frictional losses that are taking place. Now we go to state 3 right here. So you could see that I've made this clever little animation little thing, or just I've made a separate drawing. So you really can't fit this all onto one drawing. So you might want to draw these separate sketches. Don't be lazy, and draw this thing out. So now we're going to have this distance d3 that's going to be moving up the thing, right? So that's really what our goal is, to find d3. It's going to be slowed down. So it moves from state 2 to state 3. So we know at state 2, its kinetic energy is 0. We know its potential energy is only the spring potential energy, right? The gravitational potential energy is 0 because that's the datum, remember. that we chose. And now it's going to lose energy as it goes back up that D3 plus del, right? So it's going to move from here to here in that direction right there. So once again, friction is going to be the opposite direction of its motion. There is negative, but also the friction is robbing energy from the system, therefore it's negative. The kinetic energy, when it stops again at the top at 3, is going to be 0, but it's going to have potential energy due to its change in vertical position. So we put all those things in there, and we put in values, which I should have done up here. I don't know why it's not up in there. I think I might have just forgotten to put that equation back up in there. But it's good to see these in-between steps. And you could see what the contribution of this kinetic energy, that spring potential energy, and you could see that some of this, there's the D3 that we're trying to find. There's the D3 that we're trying to find. And we figure out that the distance up is going to be 8.256 meters. So it's a considerable distance, but it doesn't make it up to the 10 meter thing, right? So that's the answer. And now we also, so I mentioned it needed to be done in stages because of the deflection of the spring. And we also, so here is, wow, that's an interesting different look onto the thing. The initial energy input was this guy right here, right? So this was the initial energy that we had at state 1. And we can go ahead and plug numbers into there. We can find that initial energy. Then we can say what the energy losses are going to be. It's going to be between states 1 and 2 and between states 2 and 3, right? So here's the amount of losses that took place in Newton meters, right? That's where energy is a force times a distance, so a Newton meter is the energy. And we know that we can find what the efficiency is by subtracting from 1 the energy loss to the energy input. So this is the energy input was the energy at the first state right here. And we see that it's just about 80% efficient in this process. So for more examples, I'm going to check out the engineering course companion of parts 1 and 2 right here. And these are available in the link from Morgan and Claypool that you could find down below in the description. And also, please subscribe to this channel. And me and Wormy will be looking forward to seeing you some more. And so this is class... what class is this? Is it class 9? Yeah, I think this is class 9 out of 24. So there's a lot more to go. Until next time. Thank you.